The second part is that where we talk about the classical linear regression model assumptions. Okay, so you all remember by using the least squares regression method, we found the values of beta naught and beta 1, beta naught cap and beta 1 cap. Okay, why did we find this? What's the purpose of finding is to make decisions, it's to make inferences about the population, true population values, which is without the cap, beta naught and beta 1. Yes. So in order to, like, if we don't want to take inferences, if we just want the values of beta naught and beta 1, we can stop with this without making any assumptions. We can stop with this here itself. But since we want to make inferences or make decisions about the true population, that is the purpose of finding the estimates, basically the estimates, these are the regression estimates. Yes. So since we want to do that, we have to make assumptions about the independent variable x and the error term u. This is essential. So now we'll be going through each of the assumptions. There are 5 assumptions, CL1 to CL5. We'll go through that. Okay. So CL1 says that, this y'all would be very familiar. We say that the model is linear in parameters and not in variables. That means we have to ensure that the parameters are linear, not the independent variables or not the dependent variables. So if I give you all example, you all will easily identify what do we mean by this. Now in the first one, the model is linear in parameter. Easy, beta naught and beta 1. And what about the variables? Yes, it's linear in the variables as well. If you look into the second one, x1 square, that means the variables, it has become non-linear. It's not linear in variables. But how about in parameters? Beta 1, beta naught, it's still linear in parameters. If we take a look into the next one, variables is 1 over x. That means it has become non-linear in variables. How about in parameters? Beta naught and beta 1. That means so far these three models haven't violated the assumption of CL1. That is, model is linear in parameters. If you look at this one, okay, beta naught, yay, it's non-linear. It's linear in parameters. But how about beta 1? They have applied the ln function on that. So because of that, it is not linear in parameters. But is it linear in variables? Yes, it is linear in variables. But that doesn't matter because we are only concerned about the parameters. Next one, here it says 1 over x, x2, x to the power 2. That means non-linear in variables. But how about parameters? Beta 1, yes, linear. Beta 2, linear. Beta 3, linear. That means this model satisfies CL1. Next one, if we look into the variables, x2, okay, linear, non-linear. Here it's x2 into x3. So here it's non-linear, but x2 is linear. So anyway, we don't need to know about that. We just have to look into the parameters. So here, first one it says beta 1 square, which makes it non-linear. Okay, root beta 2 is, we can write root beta 2 as b2 to the power half, right? Again non-linear. Though this is linear, it doesn't matter because these two are non-linear. So this model violates the assumption of CL1. Next one, here if you see ln has been applied to the x value, that is x variable, but that doesn't matter. Okay, how about the population parameters? Yay, it's linear. Now this one over here, x1 is the variable, leave out that. If we look into the parameters, beta naught is linear, but beta 1, it's a power of x1. So because of that, this is not gonna satisfy the assumption of CL1. Now if you look into the last one, again it's still the same. It's basically the same concept. Beta 1 is a power of x. Because of that, it's non-linear. Therefore, this model doesn't satisfy the assumption. So whatever the equations which I've made a cross, which I put a cross on, those are the ones where the model is not linear in parameters, thereby CL1 is lost. Next one, CL2 says data is obtained from random sampling. So what we refer to this is, we say that there is no correlation between the error terms. And specifically we give a term saying no autocorrelation. Okay, so don't think that correlation, autocorrelation, they're all the same. Like in the sense that this is a specific term used in this because there's something called serial correlation as well, which is different. So we say no autocorrelation between error terms because we are obtaining the sample using random sampling. Okay, so that means if we take two errors, one is let's say ui and another one is uj, and because they are not correlated, their r is equal to 0, correlation is equal to 0. In the previous thing itself, we saw that correlation is equal to covariance of x and y divided by the standard deviation of x and standard deviation of y. So if we prove that covariance of x and y is 0, that means r is also equal to 0. So since we are saying there is no autocorrelation between the error terms, what are the two error terms which we have taken? Ui and uj. We can write this like covariance between these two error terms, if they are equal to 0, that is how we say that CL2 is satisfied. Okay, so here obviously I and j can't be equal. So you all might wonder what is this I and j. So in simple terms, if I have to explain, let's take like this value. We have spots like this. Okay, let's say this is one. How do we get the error term? Basically, error is equal to y, that's the actual value of y, which are the dots, minus the predicted value, which are the points on the line. So if I want to take an error value, it's a difference between the actual value and the corresponding predicted value, and here we get the error. Okay, let's say this is ui. Now I get another point of y. Let's say I take this is y, and this is the corresponding value of y cap, which is the predicted line. If we take the difference, I get mu j. So the correlation between, the covariance between these two error terms, just randomly we are taking two error terms, it should be equal to 0. So if you are seeing the slides, Miss might have given, if these two are equal to 0, if the covariance of u and I are equal to 0, when they are not related, then we can write something like this. Expectation of these two is equal to the covariance itself. How do we get this? How can we prove this? Is the question now. Now, in the following upcoming assumptions, we will come across something called expectation of the errors should be equal to 0. You all might even remember this. The mean of the error terms should be equal to 0. That is one of the assumptions which we take in CL4. Okay, considering that, now if I write the covariance ui and uj, how do you usually write the covariance, guys? Remember, covariance of x and y, how do we write that? We take x minus x bar, y minus y bar divided by n. Yes, this is how we do. Likewise, if we want to get the covariance of two error terms, then how do we write? ui minus x bar is the mean of x, right? So here we can write expectation of ui, the mean of ui. That's the first part. Now then we write uj minus expectation of uj. Okay, I am applying the same concept which we have learned earlier, like x minus x bar. I've got ui minus its mean. Likewise for y minus y bar, I've written uj minus its mean. Okay, now like before, I can write this part over here. We are taking the summation and dividing by n. That means we are finding the mean, which is same as expectation. So here I can write expectation. So because of this assumption in CL4 that expectation of the error terms is equal to 0, the expectation of error over here is equal to 0. Expectation of error over here is equal to 0. So what do we end up with? ui minus 0 and uj minus 0. We take the expectation. So basically it is expectation of ui into uj. So that is how we can say covariance of ui comma uj is equal to the expectation only and only when this assumption is satisfied. That means only when we say that the covariance is equal to 0. Is it so, guys? Actually, no. Okay, we can use these terms interchangeably. In the sense, when we say that covariance of ui and uj is equal to 0 or expectation of them is equal to 0, we are referring to it as no autocorrelation between the error terms. Like before, now in mean independence, we said only when that first gets satisfied, we can prove the second one. Here it's not like that. Okay, because I don't want you all to get that idea into mind only. I mentioned like that before, but that it doesn't work that way. Because of this doesn't happen. Okay, usually itself this condition is held true. Now if you see something like this, if we plot the error terms against the error terms itself, okay, and here I am plotting ui and uj, the error terms against the error terms, and if they are moving like this, if you all see it moving upward, what can you all say? Is it correlated or not? Yes, it is. It is positively correlated. In such cases, CL2 is violated. Likewise, if we plot like this, and if they are moving downwards, is it correlated? Yes, it is correlated negatively. Again, CL2 is violated. So I said there should be no correlation. That means zero correlation. So for it to be zero correlation, then the plot should actually look like this, where the points are literally random. There is no pattern. Especially we use this term no systematic patterns. Like how we say there is no significant relationship, without saying no relationship, we say no significant relationship. Right? Likewise, here we can say no systematic patterns of among the error terms should be present. Okay. Next is CL3, where they say there should be a sampling variation in the independent variable, which literally means the variance of independent variable, the variance of x, should be a non-zero value. It can't be zero. It should have a non-zero variance. Okay. Why do we say this? Because if you all remember the beta 1 equation, how do we get that? It's x minus x bar, y minus y bar, divided, we take the summation and we divide it by the variance of x only. In correlation, what did we do? We divided by the standard deviation of x and standard deviation of y. Here we divided by variance of x. Okay. Now, what would happen if all the values of x are the same? If all the x's take the value of 10, let's say, all our x's, now these are x values and the y values. Okay. Y we don't have to care about now. Let's say all our x values are the same, 10. Then what is the mean of this? X bar. That is also equal to 10. So x minus x bar, 10 minus 10 is 0. If we take the square of that, it's still 0. So here our denominator will become 0 if all the values of x are the same. If the denominator is 0, that means beta 1 is undefined. You all remember how we calculate beta naught, that is the interceptor? Beta naught is equal to y bar minus beta 1 cap x bar. So here, since we need the value of beta 1 over here in order to calculate beta naught, and since beta 1 is undefined, beta naught also cannot be calculated. Beta naught can't estimate. So this is the problem which we encounter if all the values of x's are the same. That means since there is no variation, variance of x is 0, beta 1 is undefined and beta naught cannot be estimated. So that's why we make this assumption. There should be a variation in the independent variable. In CL4, we say that the error term has 0 mean. So how do we denote that? The expectation of errors given the value of x is equal to 0. And another part in CL4 is that they say error is independent of x. Another part. Though we say it's independent, even if we say it's uncorrelated, like the error terms are independent, or we can say uncorrelated over here as well. Though in the slides Miss has given independent, if we can just prove it's uncorrelated, that's enough. Okay. So when we say uncorrelated, that means the correlation is equal to 0. Since the numerator of correlation is covariance, if we just prove that the covariance between the error term u and the x value is equal to 0, then this assumption is satisfied. We'll see how actually this expectation becomes 0 when we talk about the numerical properties, where we'll be going through the proofs and all. Alright. And one more thing, there is another part in CL4 which is CL4A. In CL4A, what they say is x's are fixed in repeated sampling. This part we have already learned. In when we are deriving the population regression function, what did we do? We selected the income levels of 100, 150 and 200 first, and after that only, based on the income level of 100,000 income level, we went to 5 households and got their consumption expenditures. Then for 150,000 income level, we went to 5 households and got their consumption expenditure. So here what we do is we start by selecting values of x. If you all want, you all can write down that and keep. We start by selecting the x values. Then for each chosen value of x, we select a sample of y values. So because of that, we can say x's over here are considered to be fixed, and therefore they are called non-random. Okay. CL5 we talk about homoscedasticity. So over here in CL5 we talk about homoscedasticity. So here cedasticity means variance. Okay, it's a spread of values. Homo means it's the same, or we can say equal. So here we are specifically talking about the variance of error terms u. Okay, so basically homoscedasticity is equal variance of u, that is the error terms, for all values of x. So according to CL4A, we say our x's are fixed in repeated sampling. So we have 100, 150, 200 likewise. Okay, then we get the y values for that. Okay, if you draw the population regression function, see the variance of the errors, it should lie in equal distance from the predicted line. Basically the variance of the errors, they are equal even while x's are increasing. Okay, when it's not homoscedastic, we refer to it as heteroscedastic. That is when the variance of the error terms, they change when the x values increase or decrease. So that would look something like this. Okay, when your x's are increasing, if your error terms move like this, I hope this is visible enough. If it's like this, see, at lower levels of x, this is your error. At high levels of x, your error has increased. Okay, likewise, this is when we draw it like this. Over here at lower levels of x, okay, at lower levels of x, if you see, error terms are quite big, but higher levels of x, error terms are quite small. So this is heteroscedastic. So when you come across heteroscedasticity, that means your CL5 is not valid anymore. Your y values are spread around the mean values with the same variance. That is what we refer to as homoscedasticity. So if we have to put it in notations, we can say the variance of u, that the error term given x, is equal to, they say, expectation of u square given x, and this is equal to sigma square. Let's try to understand what they are referring to with this. Again, in order to prove this part, I will have to use the CL4 assumption. What does CL4 say the expectation of errors is equal to 0. Okay, we will have to use this in order to prove that red color part. Okay, now guys, you all remember the variance formula. Variance of x is what? How do we write? We take the x value minus x bar, then we take the square of it, find the summations and divide it by n. Yes, so if we want to find the variance of the error, then it's literally the same. We take, instead of x, we take u. Instead of x bar, we take the expectation of u. Okay, and we square this whole thing. We take the summation and divide it by n, means we are finding the mean, which is literally the same as expectation. That means I can write expectation over here. Yes, we know for a fact, because of CL4 assumption, expectation of u, the error term, is equal to 0. So I can write this as u minus 0 whole thing squared is equal to the variance of u, which is actually expectation of u square. So see, this is how we get that. Variance of u is equal to the expectation of u square. Now, why do we put this as equal to sigma square? That is because we are showing that the variance of the error terms, they are equal to a constant. If I had written like this sigma I square, if I had put an I subscript over here, that means it's no longer constant, it refers to a variable. So when it comes to heteroscedasticity, we use this one. But since we are talking about homoscedasticity, we don't put this I subscript over here. Here, this I subscript I am removing. So it's equal to sigma square. We are using the sigma square for what? To show that variance of the error is equal to a constant. So that's it with the CLRM assumptions from CL1 to CL5. But before we end this part, I have a question for you all guys. So it goes as, does running a regression of y on x, where we have y as a dependent variable and x as a independent variable, will give the same slope coefficient as running a regression of x on y. So in x on y, x becomes the dependent and y becomes the independent. Okay, in such a case, they are asking whether our beta 1 over here is same as the beta 1 star over here. Is that so? Actually no, because why? If you look into our beta 1 equation, it's the covariance of x and y, which is x minus x bar, y minus y bar, divided by the variance of x, right? So that is x minus x bar whole thing square sigma. Okay, now if you see in our denominator over here, we are only considering x. So for example, if I give an example, it might be much easier. Now let's say our y variable is income. Let's take x variable as income. Okay, so our x variable is income and y variable is consumption expenditure. Okay, so in the first one where we take y on x, we are taking y as a consumption expenditure and x as our income. But when we do the other one, that is on x on y, okay, we are switching these two. So here x becomes a dependent variable. So in the denominator, it will be income, I'm sorry, in the denominator we will have both switch now. So income becomes y now and y becomes x now. So in the denominator first, previously we had income. Now it's not income anymore. It will be the consumption expenditure. Okay. So because of that, we do not get the same slope coefficient. So when beta 1 changes, okay, when beta 1 changes, we know that we use the beta 1 value in to find the beta naught as well. So beta naught also eventually changes. So what I have to remember is, though we take the same two variables, when we switch the dependent and independent variables, the slope coefficient which we are gonna get, they are not the same. Why? Because in the beta 1 formula, if you look into the denominator, we use the x value, that is the independent variable. So when we switch the variables, the denominator value is gonna get changed, and therefore beta 1, the slope coefficient, is gonna get changed.